gonna hit record. There. No, that's recording. All right. So yeah, like as I said, everything above the green curve is a success. Everything above the green curve or below the green curve is a false sample. This represents a very common function in math, which is called the sigmoid function. So like if you look at it correctly, that's just what it looks like, right? Like it's almost the exact same. So we're going to use this and we're going to figure out how to use this function to figure out where our points lie. Um, Again, if you know enough about mathematics, you know that if I replace x with minus x, the function just flips. So that's not something you should be worried about because, you know, what if the top should be at the left instead of the right? Like they're just weird basic things. So there are going to be some terms that I'm going to use subconsciously because I'm too used to using those. So the first is a data set. Now, a data set is a matrix of elements where every row is a particular data point. So because we're using stocks, it could be, you know, the value for day one, the value for day two, the value for day three. All of these are going to be rows. Now, every column is a feature. Now, a feature is something that, you know, you just use to predict stocks. So one thing that most people use is the opening price, the closing price, the high, the low, the volume, stuff like that. So these things are what we call features, and these will be columns. So if you can see that, that just, you know, a two-dimensional matrix or a two-dimensional list of values. So you represent this by X. Anything, any place you look at it online is also going to use X. I don't think I've seen any place which doesn't use that. Xij would represent the, you know, the value of the jth feature for the ith data point. Labels is what we're going to use. So we're going to use 0 and 1, which is what is generally used with logistic regression. 0 is a decrease, 1's an increase. Now, you can use any other thing that you want. You can use -1 and 1, 0 and 1, whatever. The only important thing to note about this is the fact that these have to be, or logistic regression is a binary classification model. So if you try to divide this into three things, it wouldn't work as well, or well, it's straight up wouldn't work, but you can combine it with other things to make it work. There's something. All right, that's the different thing. All right. So what was I? As I said, logistic regression is generally used as a binary classification model. The values of the label themselves are something that you decide. It's not really something that should really bother you that much. You can use -1, 1, whatever. We're going to use 0 as decrease, 1 as increase. Some models use 1 as decrease and 0 as increase. Again, it doesn't really matter. Now, there's something called a learning rate, which is alpha. If you've ever, I should have a slide about that. I can't. Nope, I don't have a slide about that. So a learning rate is basically, you know, you look at how well you predicted something, and then you have some errors, right? Like if you predict everything in the first try, that's fantastic. But generally, you'll have some sort of errors, which would be about how a particular thing or how off your current estimates are. So you can use those to figure out, you know, in which direction to go and how much you need to go by. So if you're walking on a road, for example, and you know it tells you that you are slightly to the right of the actual thing, but you're not sure how many steps you need to take to the left to get to the actual point. So you use something called a learning rate, which is the steps. So you figure out, or the number of steps cannot be too small. So for example, if you're walking from Purdue to, I don't know, New York, and you know that's where you start off with. You know you're much further to the west, but how many steps to the east do you need to take? Your learning rate cannot be something like 1, because taking one step and recalculating your position every time would take you a long, long time. But at the same time, it cannot be something absurdly large like 3 trillion, because at that point you're going to overshoot New York by so much that I think you'll just go around the globe. But like, does that slightly make sense? Oh, because no one's responding, I'm just assuming everything makes sense. Now, weights is something which is fundamental to every machine learning model that ever existed. Now, each feature contributes differently to the end result, right? For example, your final value might be dependent more on the opening price and the high price of a day than it is for the past, or than it is for like the closing price, etc. So how do you account for that? You score or you weigh each feature independently. For example, in a group project, right? Suppose I had to give 40 points to a group of 4 students. Now I can either assign them all 10 points, or I can divide it into a certain way that the person who contributed the most gets the most points. That's just how you use weights. Now, if you look at this, there's an x-axis and there's a y-axis, right? So this is just the sigma x. This is just the definition of a sigmoid function. But we need to figure something out differently. So before we start with that, I'm going to start creating the data set. So that is easy. If you haven't seen it, the chat includes a link to the GitHub account, which contains a notebook. So like if you want to follow through, it's just easy because right now I'm just going to copy some things and like run it into the data set so we can see what's happening. All right, so that imported. All right, this function looks very complex, but it's really not that complicated. All it's doing is it's getting stock data. So I'm just gonna run it and I'm gonna show you what you get after you run it. DJI stands for Dow Jones. There are some things that you need to know if you're working with stocks. DJI is Dow Jones, and GSPC is equal to, what was it, S&P. So like if you want to use a different stock, you can go right ahead. But what we're doing is going to be essentially the same. Give me a second. All right. So as you can see, all I did was I just got particular data values. Okay, Zoom's messing up for me. All right, there, that works. Now I'm getting data all the way from, well, I selected my original start date as 1950, but Dow Jones really didn't start back then. So it starts from 1985. This is a data frame. It's a particular data structure that's you can only use using a library called pandas. I use it because that's how Yahoo itself returns data sets. So you don't have to use it because I'm going to convert it into a matrix anyway. But yeah, so like if you can look at this, so our data point right now is this particular row right here. That's one data point. So for every date, we have a particular data point. Our features are these particular things. So high, low, open, volume, adjusted, close is what we're going to run with. Now, before we do anything, as I said, we need to convert this into matrices. So you're going to get like individual columns first. So you can use a data frame to manipulate things, but if you don't know how they work, it's going to be complicated. So I'm just going to convert those into lists. Keep in mind, open right here is a keyword. I can use this because I'm not going to use open anywhere else. So I'm also going to create a new function, which is called sign. Now, what does sign really do? Now, as I said before, we're going to classify things as 1 and 0, right? So a 1 is an increase, a 0 is a decrease. So all I'm saying is if x is greater than 0, I'm going to return 1, else I'm going to return 0. Again, I use 0 and 1 because that's how you stand, or that's the standard classification. You don't have to use that. You can return -1 here. It really doesn't change anything. Now, the next thing I'm going to do is find the labels. I don't know how many of you know generator functions. I'm going to write the generator function here. And if you don't know it, I'll just, all right. I'm just going to create a new list. Yeah. What is this? Labels.append. All right. Oh, the not defined close. Oh, I never ran it. My bad. All right. So one important thing to note here is I use the difference between the next day and my current day. which is why you use I plus 1 minus I rather than I minus 1. Now, this is something which is unique to stock market data. So stock market data is something we call time series data, in which the value of the future is inherently dependent on the current and the past values. Right now, we're going to ignore the past values. We'll deal with that if we have time at the end. So again, if I just use I minus 1, or like I replace this with this instead, the reason why that's an issue is because you're using the current value to predict the past value, and that's not something you want. You want to predict the future value with the current value. Just as so, if I'm predicting the future value with the current value, right? Do I have any label for my first data point? I really don't, because there's nothing before the first data point to predict if that's increasing or decreasing, right? So as such, I need to delete those. I need to delete the first, or sorry, I need to delete the last values because I don't know what the future value for those is. I'm not doing something else. So I'm just, all this does is it just slices it and gets everything up to the last element. There. So now if you print the length of these to make sure, these are correct. They should be the same length. They are the same length. If you have, okay, now these were my features, if you remember right. And labels was what I'm trying to predict. So if I also just do the first 5 values of labels, it should be positive if I remember right. Right, so if you notice it actually decreased for the first 3 days, increase, and then decrease again. If you go back to this, you can see that it actually did decrease for the first 3 days. So like it decreased once, it decreased twice, it decreased 4 times, and then it increased again. And then we don't have the next data set again.
Again, question.
What?
Chat. There's a question in chat.
Give me a second. Oh, colon -1 gets all the points up to the last index. So the easiest way to explain this would be, here, give me a second. So say I have A, right, which is 1, 2, 3, 4, 5. So if I just run this, so all it does is just removes the last element. That's it. I don't know if there's an equivalent Java function for it. I have not used Java in some time. All right, there's another. Oh, all right. That was, someone sent, the matrix starts at any number and it's at -1. All right. I don't know if that's a question or not. Also, if someone has a question, you can just like unmute and ask that in real time. Like, you don't use a chat because that becomes slightly annoying. All right. What next? So now after I have this, I still need to make the data set, right? So my data set was, if you remember right, my data was just, I don't have a full stop there. It was high, low, opening, volume, and close, right? Now, the issue with this is it's, well, there's no real issue with it. So if I print the first 5 values of this, right? Generally, try to complete these in NumPy arrays. They are much better. And another thing is the format is slightly off. So if you remember right, my data set was every row is a data point and every column is a feature. But in this, every column is or every row is a feature and every column is a data point, which isn't something you want. It's the transpose of that. So I'm just gonna do something really fast. So all it does now is it converts it into a NumPy array. It converts it, so this part converts it into a NumPy array, and this part just transposes the matrix. So dot T is just a transpose function. So if you look at it now, everything has 5 elements, which is exactly, every row has 5 elements, which is exactly the number of features we have. Now, after that, let's try to visualize this now. So we need to figure out, if it's going to increase or if it's going to decrease, or but what does it really depend on? So this is just a general thing that I use. I don't know about other people. Before you actually start implementing anything, I try to see what my output is dependent on, or if there's like any pattern I can quickly extract and implement, right? So I'm going to create a simple thing, which is, let's say this, and then for I in labels, if I equals 0, nope, that should be a red. Right. Now we should have the same number of colors as we had number of labels. I'm just gonna ensure that too. So 8875 is also the same. Right. So now we have this, but if you remember right, we have a 5-dimensional data set. Now 5-dimensional data set cannot be visualized. I mean, unless there isn't anything. So what we usually do is you take up, a couple of features. You can use, so we have 5 features. We have high, opening, low, volume, and close. I'm gonna try it with each individual one and then just see what happens. So I'm gonna use something called mat.lib, and the command is just this. So what it is was it's printing, or it's figuring or all right, the y-axis or the x-axis is the day, the y-axis is the closing point. Now if it's a red, it's a decrease. If it's a green, it's an increase. Now there are certain things you can see is like, if you notice, all the peaks are red, which makes sense because of the fact it's a peak. It's going to decrease the next day, so it has to be red. And all the valleys, which like the lowest point in anything, is green, because if it's the lowest point, it has to increase after that, right? So it's just going to be green. But does this give you any information? It really doesn't. So try something else, maybe volume. So that just looks haphazard. And I mean, there's nothing really important going on there that you can extract, at least. Again, high is a similar thing as close, which makes sense because high is dependent upon the value of, you know, the closing value from the previous day. Similarly, opening is slightly more different because if you notice it, right, like if you notice, okay, I'm gonna copy this, and then I think that's gonna be much more important. Is it running? It is running. So the difference between these two is slightly subtle. If you notice in this one, all the bottoms are bright green and all the tops are bright red. So like you can see that red is somehow always above the green pearl. But in this one, you can see that they're much more mingled. Like there's a much more equal distribution between them. Now that's because of there are things in the stock market which are not represented in the data itself, and this is only for day trading. There is no off-market trading involved in this, and Dow Jones is dependent a lot on off-market trading and other factors, but we're not including any of that right now, so we'll just ignore that. So the next thing we need to do is we look at the shape of the data, which is just this. It's a numpy function, and if you remember right, it's a numpy array too. So like it has to be like data.shape is a particular, or dot shape is a numpy function. Just don't try to use it with a list in Python. That'd be strange. Um, Now another thing that you've probably heard about in machine learning is a train test split. So we generally train on a certain amount of data and we test on a certain other amount of data. For most data sets, we use something which is incredibly common, or we just randomly take 75 to 80% of the data and then you train on that and then you test on the other part. The reason why you can't do that in this is because it's a time series set of data, right? So if I randomly take some, I can have in my training set, I can have something from 2000 and something from 2020 and then something from 2003. But my test set can then be something from like 1985 and 2001, which is completely shuffled. So at that point, it makes no sense because if you're training on values in the future and you're testing on values in the past, you're inherently passing information from the future to the past. Now, is that something you can do in real life? Nah. So we're just gonna try to prevent that from happening. So how do you do that? So we're gonna do. Oh, all right. I did not know that was a thing. All right. So what we're gonna do is we're just gonna get first. I'm just gonna say split is 0.8. Now, split is 0.8. I can just do train or non-samples. Length of data. Not shape. 0. All right. I want to run this. Not sure that. Oh, yeah, my bad. I used length and then I used data.shape again. So what this means is I have 7,100 samples in my training set, and then how many ever is left, which is how many were there? 8875, so 107, 106, 1,600 samples. All right. So if we have that, we now need to split it. So I'm gonna do train is equal to data colon ns, and then test is equal to data ns colon. So again, it's not doing anything strange. All it's doing is just splicing it. So it takes the first ns, which is 7,100 samples. It's going to take the first 7,100 samples from data and put it in a new numpy array called train. It's going to take the remaining samples and put it in a numpy array called test. The way splices work in Python is you take the initial value. So you can put in a 0, it doesn't really matter. The left value is inclusive, the right value is exclusive. Now, if there's no value in here, it's just going to take in everything up till the end. So if you now look at this, right? So if you can see, like the total of this should be 8,085, 8,875. Now, after we have this, we need to, again, split our labels equivalently, right? So I'm just going to, again, just do the same thing. All right. Now, there is something which is very important, which is what we call pre-processing. So pre-processing in stocks or any other time series data has to be taken very importantly or has to be taken very seriously, because if you don't do it correctly, again, as I said, you'll be passing information from the future to the past. Now, you can't, like, at least in real life, I don't know of a way to get information somehow from the future, to the present. Right. So wait, where was I? Yeah. What you need to do is figure out a way to pass information, or not pass information, but convert these values. So we're going to try doing it two ways. We're going to normalize this data and we're going to leave it as it is. So what does normalizing mean is, so say I have some values, right? Say I have some values between 0 and 100. Now I can normalize it in such a way that now this range of values will just be from 0 to 1. So I'm just scaling them all down such that the mean is scaled down, but the standard deviation of the values or the distribution of the values doesn't really change as much. It doesn't change at all, actually. The reason why the standard deviation would change is because the values are smaller, but that is a con. There is some math involved in that, but don't worry about it. So yeah, as I said, we're gonna do it without normalization and with normalization. So right now, let's just hello. Someone said something, and uh, um, so we don't use 0.8 as a split. So we're using 80%, right? Now 80%, if you know, it's just 0.8. So we're using 80% of our data as our split. So 80% of our original data is training, 20% is testing. In other models, you'll also have to account for something called validation data. You don't really need it for logistic regression, so I'm just going to skip over that. If you have time, I will go over it. All right. So the first thing I'm going to do is I'm going to just normalize them. So we see how, when you normalize them, how the values look like and other things. So again, if you don't know your functions, all this does is going to find the minimum value of the entire matrix. Now, NumPy is a fantastic matrix library. So when you do np.min on a matrix, it's going to find the minimum of all the values along in the column and then create a new vector. So if I, for example, if I do min.shape, right. So as you can see, it has 5 values, and like each value would correspond to the corresponding column. So train or the minimum for column 0 would be again in train min 0, stuff like that. Test min would just calculate tests, and then so the way you calculate normalization for anything is, I'm just going to add it here, a minus min divided by max minus min, where a is your value. So all it's doing is, just scaling everything down. So if, again, just goes from 0 to 1. So the minimum value is min. So min minus min is just going to be 0. Maximum value is max. Max minus min divided by max minus 1 is just 1. This is linear, or it's not really a linear operation. But again, details of how this works and why this is useful is a really long talk, and why you use it in pre-processing for numbers is, again, another really long talk. So if you have time, we'll come back to it later. So I'm just going to normalize this. Now let's see if I can just create. It doesn't work. Now I'm just going to create the sigmoid function. Okay. Now there's a reason why I'm doing np.exp minus x rather than just 1 divided by 1 plus e star star minus x. The reason is super simple. NumPy, as I said, again, it's a library that or used only for matrices. So if you pass in a vector, and I'm assuming you guys know what a vector is, or if you don't know what a vector is, it's just a list, a one-dimensional list or one-dimensional array. Now it's taking that array and then it's just going to apply np.exp on all of those. So for example, if you have, say you have a is equal to 1, 2, 3, 4, 5. Actually, I'm just going to do 0 as well, because, right, and then I do print np.exp a. All right. I don't know why that's stuck. Am I still connected to the internet? Hello? Oh, shit.
You're good.
Oh,
On the
okay.
internet.
Oh. All right. Yeah, so Colab just crashed. I'm just going to read on all pieces of code. Oh. Yeah, Colab just crashed entirely for me. Is it working? Is it not working? All right. I'm gonna switch to Jupyter Notebook because I think that's just gonna make my life easier. Guys, Colab stuck. All right, give me a second. New share. All right. Can you guys see this? So at least so
Yeah.
far, like it's just the same things that we've been doing so far, except I don't have the. Oh, yeah. There's there. There's so much in the chat. All right. Again, so right now I have it normalized. Later on, I'm gonna show you how to do it or why you normalize it. And like rather than explaining the math behind it, we're just gonna see what happens with the results. So this is just the sigmoid function, and as I was showing you guys there. So if I have an array, right? I'll just run this statement right there. So if you can see this, all it's doing is it's taking every value in there. So every value inside A, and then it's just tracing or E to the whatever value it's in, and it's just going to return new numpy array. The reason why you do this is going to be explained much later. I suggest using this, even though we don't really need it, and you can just calculate e to the minus x normally, or using any normal math function. But np.exp is significantly faster over multiple runs, and as you'll see, we're going to run it a long time. Yes, we do have to install that locally. All right, so I'm going to use a likelihood function. I use log likelihood. You don't have to use it. Now, again, what is likelihood? For that, we'll have to go back to the presentation. All right. Now, log likelihood is basically, so, you generate some sort of weights, right? And then you figure out, oh, actually, I should get back to that after some time. Let that be as it is for some time. I'll explain that in 2 minutes after you're done with this. Now, I wanted to write this out in front of you, but I guess because it's already started and I can't use Colab anymore. All right. So we're going to create a new function called logistic regression. Now it's going to have, okay, you need these two input variables because they're just x and y. X is your input data, y is your labels. So if you remember right, x is the matrix which contains open, low, high, close, adjusted close, volume. Intercept, well, you guys have seen a line, right? And if you remember how weights worked, we're going to try figuring out how that works too. So why you need an intercept. So if you go back to Sigmoid function, you see that while I'm plotting it, I'm creating a probability. I don't need a probability in 5 dimensions to predict one thing, right? I'm only predicting the closing label. Now, if that is the case, I've been predicting one dimension, and to get a one-dimensional value, I'll need to put in a one-dimensional input into the Sigmoid function. Now, one-dimensional input is just a single number. So how do I create that single number? If you remember, if you remember, I talked about weights and how you weigh each feature independently and differently. So I'm just gonna, so the way you calculate it is just weight 1 multiplied by feature 1 plus weight 2 multiplied by feature 2, weight 10 multiplied by feature 10. If you look at at any online thing, they're gonna use, instead of the weight matrix, they're gonna use a theta matrix. They represent the same thing. It's just the notation that's been, used for the past 78 years. So xi represents the ith feature. Lowercase x represents your data point. Uppercase x represents the matrix, the data set. Now, the last value that you have is wn times 1. It's not multiplied by any feature. It's just a constant offset. If you look at any line, which is y is equal to mx plus c, right? You have m, which is the slope, and which is the weight of the x, and c, which is a constant intercept. You generally use that, just in case like you're slightly off or something. It's always better to have this because, for example, if your model say did not need it at all, over time that weight would just go to 0. Now we come to log likelihood. So you have some particular set of weights and you have a particular data set which each with their y values. You need to figure out how good your estimation of your data set is. So what you do is you find the log likely or find the likelihood, which means you find the probability that given a set of weights and you start generating data points, you get the same data set as your original data set. Now, probability is, if you remember something, it's between 0 and 1. And multiplying a number between 0 and 1, thousands and then thousands of times, as our training said, it's 7,100 times. will give you a number which is almost close to zero. So unless you use specific libraries to calculate it, most programming languages would just give you zero for the likelihood. As such, we use something called log likelihood. It just, takes a log of every probability and multiplies them all. Now, there's another interesting thing about log is if it's log of AB, it just becomes log of A plus log B. That's a feature that we're going to use later on. Now, let's go back. Once we've explained this, we're almost done and we can actually start coding this. All right. So I'm going to use a D for intercept of true. What, again, so if I have an intercept, now if you remember right, like I don't really have an intercept anywhere at the beginning. All right, someone's sending chat messages. All right. So if you have an intercept, all it's doing is we need to add that as another feature to our data points. We don't have to. It's just better if you do. So that way, you have a much better idea of what your data set actually looks like after the entire thing. So if you remember right, it was wn multiplied by 1. So I'm going to create an array of np, or just ones. np.ones is a numpy function that just creates an array of ones of a particular size. I'm using length x because that's our data set, and I'm reshaping it to be a particular size. NumPy also has an annoying feature where if you pass in a one-dimensional list and you convert that into an array, it's actually a non-dimensional list, and that's a whole different technical issue that we're never going to go in. What this line does is it just stacks them together. So our feature, or we had columns, right? We can't just append all our ones to one column. We have to append one single one to every column. So all this does is it takes that column and just adds it to the very end. That's it. Now you're gonna have to start with some default set of weights. You can start with all zeros, you can start with all hundreds, you can start with threes. It doesn't really matter. Eventually, after running it enough times, they should all go to the same value or converge to the same value. Most people started with zero. That's another standard thing. But how do you actually do it? So we're going to, just run it infinite, or just run it some particular iterations, and then we'll see how the results are. If you're ever doing it in research or doing it professionally, you run it till convergence, which is, that like after at that particular value, no matter what you do, it just won't change. That's the best value you can ever get. Um, yeah, this is another important thing about scores. So I'm going to create a new matrix here. See, I had something, right? Like I had a set of matrix 1, 2, 3, oh, wrong, and then like 4, 5, 6. I really don't know what the hell constant. All right, and then I have my weights. Now, in this, if I have two data points, which is one is the row 1 to 3, and the second is the row 4, 5, 6. And I have three features, 1, 2, and 3, and or column 1, column 2, and column 3. Now, if I need to have some weights, right? So say I have weights 1, 4, and 5. Now, eventually, I'll have something like A star weights, or, let's say it's scored 0 is equal to. Also, whatever I'm writing here in this cell is not really actual Python code. If you execute it, it's not going to work. It's just going to throw you a syntax error. So scored 0 is just you multiply the corresponding weight with the corresponding feature. So it's 1 star 1, 2 star 4, and 3 star 5, right? And then again, similarly, you'll have scored 1, which is going to be something like 4 star 1, 5 star 4, and 6 star, 6 star 5. Now, I mean, you can do this individually for each one, but you can also use matrix multiplication. So if you notice, all I'm doing is, take this value and multiply it with this particular value, right? Take this value and multiply it with this corresponding value. If you know any vector math, that's just taking the dot product of those two values.
Dan,
Also,
there's a question in chat for you.
oh, yeah, give me a second. That shouldn't be comma, that should actually be a single value. We have a question about intercept. Oh, what is the purpose of having an intercept? So the purpose of having an intercept is, again, just to, have a constant offset. So if you have the line y is equal to mx plus c, if c is equal to 0, it can only go through origin, right? Now, if it can only go through origin, you're limiting a lot of different possible values. As such, you generally have the intercept to move that line around. It's something you take from linear regression, from which the entire series of logistic regression comes out. Let me see if I can just open Desmos. Ah, shit. Where's Desmos? Now, say I have y is equal to x. So if you notice this, it can only go in this particular line. So if all our points were such that, they lied only to this particular area, that would be great. Or if they only lied to this particular area, that'd be great. But sometimes, they just don't. But say there's one point, there's one good point that lied here. Now you can fix the model in such a way that it splits it accordingly, but you really don't need to. What happens if you just move it up by one? Like, again, it's a thing that came out from linear regression, and it is used in logistic regression. And as I said, like, if it was not needed, it would just automatically go to 0. So you really don't need to think too hard about that. If I have time, I'll explain that in more detail too, I promise. But right now, I just want to get the basic codes done. Right. So this is my score, right? Like, if you know dot product, this is just the dot product of weights and a, or a of 0 and a of 1. NumPy, or a dot product of a vector with a matrix, is a well-defined thing, and that's what we're going to use. So I'm just going to create all of this in one single statement. This is going to create a new matrix called scores, which just takes the dot product of everything at the same time. Now, prediction. So these are particular scores, but you need to pass these into the sigmoid function to find the probability, right? So I'm just going to pass all these values into sigmoid. Now, remember when I said that you can np.exp all the way up here just finds the exponent of all the particular values. So again, instead of going over it in every line, I just find the sigmoid in one step. Just goes over it in one line. Now, the log likelihood prediction calculations is, I'm not sure how to explain those because that's a lot of math involved in there. For now, just, all right, let's try it this way. So why is some number between 0 and 1, right? And prediction is, again, is a probability symbol. It's not really any sort of labels. We need it this way because we want to guarantee that if it's a true positive, then those values are super high, and those probabilities are almost like 0.99%, that okay, that's what I'm talking about. But again, at the same time, if the probability is super low, which means that it's probably a decrease. Oh, I should probably also explain what the probability is. The probability is the value that is going to increase. So 1 minus probability is the probability that's going to decrease. The higher the value the probability is, the more likely it is for it to be a increase day. The lower the value of that, the likelier it is for it to be a decreasing day. So when you, again, deal with this, so you're just going to subtract those two, and then, as I said, you need the probabilities to be as close to 1 or 0 as possible. You want those to give a very nice regression graph. If you can get it, like, to be perfectly done, like, or perfectly 1 and perfectly 0, you're just done. If you actually convert these to zeros and ones, you're just gonna fail. So don't do that. To calculate the log likelihood, you need to do y minus predictions, and prediction is the set of probabilities. Now you create something called the gradient. Now, again, why do you have a gradient? So gradient is the slope of a curve, if you remember different or any differentiation. It's basically just doing all it's doing is it's taking the data set and finding all those particular values and then multiplying those with the particular probabilities. Why do you do that? So you want to ensure that, if the probability was almost 1, then that part of the vector was doing perfectly fine. There was absolutely no issue with it at all. But if that part was off, right, then you need to make sure that it increases by a much more important factor. So if I was off by 1, I don't need to increase my or change my values by a large amount. But if I was off by like 100, I need to increase my value by a large amount, right? Or if I predict one when it was clearly a zero. So all it's doing, the gradient just helps in figuring out how much I was off by. Now, what's my weight? So you don't really use likelihood to actually figure out your probabilities. Likelihood is used to compare two models. So I'm going to use again likelihood only to measure if I was better off than before or if I'm worse off than before. That's it. Likelihood is a negative number. The closer it is to zero, the better it is. That's another important thing to know. So, sorry, what? Okay, there was a noise. Again, I'm just in this step, I'm just updating the weights. I'm gonna add to the slides about what the gradient really is, geometric wise, because I think that's gonna be much easier to do. And every 1,000 steps, I'm just putting out the likelihood. That's all I'm doing. And again, I'll just write on the weights. Oh, I did my train labels and test labels here, and that's actually all it is. I'm just gonna call the function. My learning rate, if you can see, is pretty small. I can make it even smaller. Again, I'll do it with two different or with multiple different values to like figure out which value of learning rate is the best. Oh, I keep on forgetting that I need to run these things again. Yeah, let that syntax run. Oh, just so you guys know, I'm running it, I think, for 100,000 iterations. You don't have to. You can just run it for like 1,000 iterations or something. So because of the fact my learning rate was so small, right? My original value started off with 4920, and then it started off to like it went to 4903, and then it just kind of stabilized. If you can see, it keeps on consistently decreasing or consistently increasing, which is good. Like the higher the prob or the log likelihood is, the better your model is. Now, if I change it to something super small or super large, say zero point 0.01, which doesn't seem like a large number, but if you can see this is all over the place. It started off with 13,471 after 1,000 steps rather than 4,920, right? And then it went all the way to 16,000 and then, or 161,000. And this keeps on increasing and decreasing very haphazardly, which means this is too large a load. So again, these are things that you get better at with practice. There's no silver bullet, but the way I generally do it is I try a large learning rate that I know is going to be bad, and then try a super small learning rate, which one is going to be too slow. And then I just kind of use like a binary search algorithm to figure out the perfect learning rate. Most people just automate the entire process, and there's multiple ways to do it. I'm going to use the same learning rate as just like 10 to the minus 5. Let that run. All right, now it's done running. So what now? We need to calculate accuracy. And all right, again. So I'm gonna get the training accuracy because it's super easy. If I have the intercept on, and if you notice that right there, I do have my intercept on, which is, yeah, right here. So as such, I'm just, again, because my original training data did not have that once, I'm just gonna edge stack it or just add it as a column. And if you see these, like at the end of it, these are my weights. And I never actually got my accuracy right in that cell right here though. So my training accuracy is 53.36%, which isn't great, but it isn't terrible either. Most people think stock market is basically flipping a coin. Flipping a coin is 50%. So your training accuracy is slightly better and, slightly great by like 3%. You're better. Instead of flipping a coin, you can use this model and still win 3% of the time more. And your test accuracy is 54.4%. It's not too good. It's not terrible either. Again, much better than what it is. Trying to predict the next day. Yes, that is exactly what we're trying to do. Give me a second. All right. Now, what happens if you had a really large learning rate? Or actually, let's try reducing the number of iterations first. So I know I had a large number of iterations there. So I'm just going to reduce those iterations. And if you can see, like my training or my accuracy did decrease by 0.01%, which isn't a lot, but over the course of like 1,000 days, that's one more day you could have made a success in. Also, there's some really good questions in this chat, and like I'm gonna get back to those in 2 minutes. It's like, all right, because now the next thing that we're gonna do is fuck around with the learning rate. So if you can see, oh, that actually didn't change at all. That's interesting. So even with a higher learning rate, even though log likelihood is much worse, our actual values didn't change, which may be because the number of iterations is too small. Yeah. Nope, doesn't change. So maybe for this particular set of values, it doesn't really matter as much. And the next thing we need to do is figure out what happens if we don't normalize it. So I'm just gonna go all the way back and get my data again because I normalized the actual data. Not a smart move. All right, all right. Now this is just a string search and execute. Just convert that all. All right. That isn't even a normal thing. Oh, yeah. So if you can see this, the values were so big that they just overflowed to infinity, which means our model's very bad. And our values are insanely large. All right. If you did not notice that, that decreased by a solid 0.02% right there. Again, because of the fact this is a very simple model, normalization doesn't make that much difference. But at least in the all right. So the reason why I decided to use this design in the first place is because this is one of my research topics. We don't use logistic regression. It's pretty simple to implement, and I mean, it's not really the best thing to do. The reason why we do anything like this, or is just like a simple, a basic thing, or like a first approach, kind of to see what's happening and how it's happening. In my thing, like in most of the research work that I've done, if I don't normalize it, my accuracy is anywhere between 40% to 60%. But if I do normalize it, my accuracy is somewhere between 70 to 90%, which is much better than this. All right. Now the question in the chat. All right. So can we increase accuracy by increasing the number of previous day candles and increasing layers? Yes, you definitely can. The more data you pass into logistic regression, the better it is. In fact, we can also just try that right now. Um, so this was a very linear approach, right? We never really did anything interesting. So what happens, you can create a new feature whenever you want. So say I have this, I have np dot array close, and I have now I can just do f1 comma f2 and then just list. No, my bad. That should be you. All right. I think there's something in the chat. All right, I'll get back to those in like 5 minutes. Let me just or actually, but realistically, the reason why a lot of people use logistic regression is so right now we have a one-dimensional model in a sense, or not one-dimensional, five-dimensional, but everything depends linearly on opening, volume, close, whatever. The easiest way to deal with that is you start taking some other things and then you start multiplying them. raising them, whatever. So instead of just having closing and volume price, you decide, what's going to be a better idea. I can just make it something like a square, or instead of just dealing with close, I'm going to deal with close squared, stuff like that. So it's a linear combination of open, volume, close, close squared, and that's a significantly different idea. uh, Again, it's the same idea with linear regression, if you've ever done it, which is, I think, the most basic machine learning model there is. I'm going to try answering questions in the chat. How do changes in the implied volatility affect the accuracy of the model? So the thing with stock market is volatility is increasingly, or it's not increasingly hard. It is a strange thing to predict with using just these five values. You need candles, and you don't just need a day's candles. You need to use at least like the previous 1 week's candles to have any idea of how good volatility is. Using or Because of that, because I'm just using 1 day, the volatility does not really affect it as much. It should. It's not assuming any volatility, which is one of the reasons why the accuracy is so bad. Adding volatility to it is one of the first and most basic things that most people who deal with stocks do. What are some better models that you can use? All right, that's a there are multiple great models that you can use. The easiest one to implement is probably going to be decision tree. Now, a decision tree is not really that hard to implement. All it does is it takes in the particular values and see, okay, if volume is greater than 300 and if opening price is less than 200, then I think it's going to increase. It creates a large tree of decisions based on this. Again, it's a continuous value spectrum, so it can be much more specific to do that. Based on that, it's just going to increase stuff like, or based on that, I think the best research paper that I'd seen had an accuracy of 62%. I might be wrong because I'm remembering this from the top of my head of a paper I read 2 years ago. Um, there again, you can use a neural network. I use a deep neural network with 7 layers, and again, that's a very, very big neural network. But my accuracies are generally upwards of 85 to 90%, which is fantastic. Um, what would you have to do to increase the number of layers in a model? Increasing the number of layers in a logistic regression makes no sense. Layers comes in when you start dealing with things like neural networks. Logistic regression by itself does not have a layer. What you can do instead is use logistic regression as a layer. So you use logistic regression to create a set of probabilities instead of just one. Maybe you try to predict all five values, or you try to predict all five markers. You try to predict if the opening price is going to go up, the low is going to go up, the high is going to go up, the volume is going to go up, or the close price is going to go up. You predict all those probabilities and you use those and put it in I don't know, a linear regression model, and use that to figure out if those particular values correspond to a increase or a decrease. Yes, LSTM isn't now. LSTM is a very interesting thing, and again, if you ever go to any neural network or any self-respecting neural network that deals with stocks, they're going to use something called an LSTM. Now, I don't know how many people of you know what an LSTM is, but so as I said, right, like stocks, the value of any stock depends not just on the current day values, but also for the past 15 days or past how many ever days. So if I think, or if the next 20 or like last 20 days have been a constant decrease in stocks, I don't think the next day is going to increase either. I think it's going to decrease again. Does that, if that makes any sense? Based on that, what an LSTM does is it takes the data from the past X days. You define the size of the LSTM. It takes the past data and tries to use that as another feature to your current value. So instead of dealing with just 1 day at a time, you're dealing with like 30 days. And you're using those 30 days to predict the next value. It's not really 30 days. It's a constantly evolving structure. And or the 20 days pass has less weight than the weight at the 19 days pass. Or basically, the values at the values yesterday are much more important than the values 20 days ago, if that makes sense. That's how most LSTMs are implemented. Implementing an LSTM from scratch is super annoying, and I do not recommend it. If you are going to use it, just use TensorFlow. I think it's like a two-line implementation using TensorFlow. But yeah, LSTMs are gaining increasing traction to predict stock markets. Again, the best one that I've seen with even with just an LSTM is around 70-72%. Now again, random forest is just much better than a decision tree. If you know what a random forest is, then it's just a decision tree, but or multiple decision trees, and then you're just doing polling of those. Realistically, you can sometimes use pruning on those to get even better accuracy, but overall, I don't think a random forest would ever give you less accuracy than a decision tree would. A G-boosted decision tree, I've never tried one of those. I should try it sometime. But I've never tried one of those for stock market prediction. I have had to do it for other classes. Um, I can't, because of the fact I've never tried it for this particular data set, I can't tell you if it's going to increase accuracy or it's going to decrease it. So yeah, I'm sorry, but I can't help you with that. But again, logistic regression is just like going back to the topic. Logistic regression itself is not it's a starting point. It should not really be your endpoint. And there's a lot of things in this part that you can't really do in things. So if you remember, I normalized the data set, right, to get accuracy. Now, in this case, it doesn't really matter. But generally, you can't normalize a time series data because of the fact that if you do, you're passing information from the future to the present or from the future to the past. Where's my normalization? All right, that's my actual normalization code. All right, there. So in this, when I do np.min and np.max, my minimum and maximum can be in the future of my current value, right? So when I do train minus train min and train max minus train min, I am implicitly, or I could be implicitly using values from the future to predict my current values. Again, that's incorrect, and you should not be doing that. In this case, using normalization and not using normalization doesn't really affect it as much. So I guess it doesn't really matter. But generally, it's a bad idea. Don't ever do it. Or I do it, but there are like much better ways to do it. I don't think you'll find it online because like that's something I came up with for research. As such, I don't really think I have any other things to discuss about this. So, do you guys have any other questions, or can I just stop?
Oh yes, and when are you going to send a YouTube link, the recording link?
I think that's just like Virat. Do you want to answer that?
Yeah. So
Yes.
we'll be sending out soon, maybe hopefully before Friday. We'll be sending out the PowerPoint presentation as well. Also, please be sure to fill out the Google form link that I just put in chat. That's the post survey workout survey for the workshop. So your email, everyone on the email list will, get all the information, and it'll just be easy for us. And it's a feedback link as well. So we'll greatly appreciate if you can just sort of talk about, give some feedback and whatnot.
So you're going to send both of those through mail?
Yeah, we'll send it out through mail, and this will be on a Slack as well, and we'll probably put it on our Facebook as well.
Okay, thank
So
you.
just keep a lookout for those.
I'll keep an eye on that.
Right. So yeah, logistic regression does indeed account for like disparity in the training set. So if 95% of your values were, that you predicted were going to decrease, then your logistic regression weights would just account for that in such a way that it's gonna, if it can find a set of weights which would give you a higher accuracy than 95%, then it will take those. Otherwise, it's just gonna set everything so that it just always predicts decrease. So if that makes any sense, because like I'm not sure how to explain that, but if you know that 95% of the values are going to be false, right? You can, if you can create a model which is better than that, it's going to try to create that model. But if you can't, worst case is just going to make everything that, if that makes any sense. All right, I'm gonna.
And there's a
So
couple
gonna-
more questions.
There are a lot of questions in the chat.
Yeah. Yeah.
Should I just stop recording because I don't know if the chat gets recorded?
I can save the chat.
All right, then I'll stop recording. Wait, do I pause or do I stop?
I guess stop.
All right.
Yeah.